Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 22, part 2. We will continue with the numerical problems. In the part 1 of the lecture number 22, we have solved two problems pertaining to the product load. So in one problem, we have calculated the sensible heat load above freezing, below freezing, and also the latent heat load. Since that product was chicken, so there is no respiration load. So Q4 is equal to 0. In the next question, that is just before I concluded the previous lecture, the product used was green peas, but it was cooled from particular temperature to say 4.4 degrees centigrade, which is above the freezing point. So there is no requirement for the calculation of latent heat load as well as the sensible heat load below freezing. So Q2 and Q3 are 0, whereas Q1, and because green peas is a live product, the respiration load is applicable. I have calculated the Q4 respiration load also, and the total product load is Q1 plus Q4, as Q2 and Q3 are 0. Now, in this lecture, let us solve the numerical question pertaining to infiltration load. So this is the third numerical question. Estimate the infiltration load for the following data. So the inside design conditions are given. 3 degrees centigrade dry bulb temperature. So inside conditions are 3 degrees centigrade dry bulb temperature, 90% RH. Outside condition is 40 degrees centigrade dry bulb and 20% RH. Dimensions of the door are given. The width of the door and the height of the door, 2.44 meter and 2.74 meter respectively. Assuming the door opens for 15 minutes per hour for a shift of 12 hours per day. So let us solve this problem. We'll do one thing. I think the calculations are also, yes. So this is numerical question number 3. Question number 3. So the data given are with the door dimensions. Width is 2.44 meter. Door dimensions are given data. Door dimensions are given. That is, width of the door is 2.44 meter. So width of the door is 2.44 meter and height is 2.74 meter. Height is equal to 2.74 meter. These are all the dimensions of the door. T1 is 3 degrees centigrade. That is the inside condition. Outside condition is 40 degree. T1 is equal to 3 degrees centigrade and T2 is equal to 40 degree centigrade. And relative humidity, it is represented by the letter 5. Let me write it again. Relative humidity is given 5.1, that is equal to 90%, and 5, it is 20%. Inside is 90, outside is 20. 90%, this is RH, and phi2 is equal to 20%. So relative humidity is represented by the symbol RH. Sorry, phi. So this is the symbol which is used. It represents relative humidity. Sometimes it is written as RH. In symbolic representation, phi is the symbol which is used. So, if we recollect the formula which has to be used to determine the infiltration load or the ventilation load. Infiltration load, we need to calculate the velocity using the formula 0.0606 into height into delta T, that is square root of this one. This is the formula I discussed when I was taking the theory portion of this one. So let us calculate the velocity. Step 1. Velocity, that is capital V, that is equal to 0.0606 into height into delta T, that is to the power of, so this is nothing but 0.0606 into this is the square root term h into delta T, 0.0606. Height should be substituted in meter, not in centimeter or millimeter. It is given 2.74 into delta T is 40 minus 3. 40 minus 3. So the velocity comes to 0.6 meter per second. 0.6 meter per second. So whenever we are calculating the infiltration load or the ventilation load, the first step is to determine the velocity. Infiltration load is the load due to the leakage of air through air gaps, cracks, either through ceiling or walls or floor, through the doors, etc. Now, the formula to determine the infiltration load is rho into density into velocity, density into volumetric flow rate multiplied by delta H. If you want to know delta H, that is enthalpy of the outside air and enthalpy of the inside air, which is not given in the problem. So in the problem, the two properties of air are given for both outside condition and inside condition. So with the help of psychrometry chart, we can find out the enthalpy of the air. So the next step is since enthalpy of outside air and inside air is not given, it has to be determined. It has to be determined using psychrometric chart. Psychrometry chart. METRY, psychrometry chart. So let us write the given condition. At temperature T1, 3 degrees centigrade and dry bulb and 90% RH. At dry bulb temperature equal to 3 degrees centigrade. So this is nothing but T1, or let me write it as T1 itself. I have mentioned the temperatures T1 and T2. So T1 is equal to 3 degrees centigrade. Relative humidity is equal to 90%. Enthalpy at H1 have to be found out. Similarly, at T2 is equal to 40 degrees centigrade. relative humidity is equal to 20%. H2 have to be from the psychrometric chart. From psychrometric chart, so here I have taken the values I have mentioned the PPT. I will explain with the chart how to take these values. H1 13.9 and H2 64.6. So this is the psychrometric chart. In case if the values are not clear, if the letters are not clear, so just to make the learners to understand easily. So this is how I have just represented sample chart in the PPT. X-axis is the dry bulb temperature. This is the dry bulb temperature. And this is the specific humidity. This is represented by the letter capital W. Kg of moisture present in 1 kg of dry air. And these curves are called relative humidity. These curves are called relative, that is phi. If we take the inside condition, 3 degrees centigrade, so we can, this is dry bulb temperature in degrees centigrade. So we can fix the point here, I mean corresponding to 3 dry bulb temperature and relative humidity, we can fix the point. We can fix the point. For example, T1 is equal to 3 degrees centigrade and phi 1 is equal to 90. So this is the saturation curve. This is the saturation curve. That means here the relative humidity is 100%. Phi is equal to 100%. So 90%, this is the 90% line. This is the 90% line. Here phi is equal to 90%. So as we move towards right side, it will come next 80, 70, 60%, etc. So this is the saturation. So let me write this here. This is the saturation curve where at this point phi is equal to 100%. So this is 90 and this will be 80 and so on. So the intersection point of 90%, intersection point of 90% and 3 degrees centigrade, if we read the value, it will be H1. Again, where to read the enthalpy value? In the next chart I have given. So this is dry bulb temperature, this is specific humidity. There is one scale outside the saturation curve. This is called enthalpy scale. This is the enthalpy scale. Enthalpy scale on a psychrometric chart. So suppose if this is the intersection point, we have to draw the line parallel to wet bulb temperature line. Wet bulb temperature line. So let me go to the graph. This is the enthalpy scale. This is the actual chart. This is the enthalpy scale. This is the x-axis is dry bulb temperature in degree centigrade, and right hand side y-axis is specific humidity, that is W, specific humidity. This is the 90% curved line. This is the 90% curved line. This is 90% curved line. So this is the 90% curved line. 90% RH. So we can find the intersection point. This is the wet bulb temperature line. I think the lines may not be clear, but in case when you use the psychrometric chart in the physical mode, you will be able to see it clearly. Just to have an idea, I have enlarged the chart in the PPT as much as possible. So these are all wet bulb temperature lines. There are inclined lines are there. These inclined lines are called wet bulb temperature lines. Once we fix the point, the intersection point corresponding to 90% RH and 3 degrees centigrade. So from that point, draw a line parallel to the wet bulb temperature line, any wet bulb temperature line that will intersect here. So we can read out the enthalpy value. If we go by this chart, suppose if this is the point, if the point is coming here, the point is coming here. So one can draw the line like this at any angle. So that will not give the correct value of enthalpy. So from here, the line to be drawn, this is the line drawn parallel to the wet bulb temperature lines. So this value will say, for example, 13.6 kilojoule per kg. 13.9 kilojoule per kg, which is around 14 kg. 14 kilojoule per kg. So 13.9. This is how we have to take the enthalpy value. This is just only a sample. We can use the actual chart. Since the letters are not clear in this chart, so I have just explained with a sample one. Similarly, for the second, at a temperature of 40 degree and 20% RH, H2 you will get 64.6. For example, so you may get that point somewhere else here. Somewhere else here. Suppose, and this is point 1, state point 1, this is state point 2. From here, draw a line parallel to wet bulb temperature line. So this line also should be parallel to line to be parallel to wet bulb temperature line. So this is the enthalpy scale. This is the enthalpy scale. Let us see the H2 value. It is around 64.6. 64.6 kilojoule per kg. So both these lines, enthalpy lines, should be parallel. There are a lot of wet bulb temperature lines. You can refer any one wet bulb temperature line and draw parallel to it. Otherwise, if you draw in any angle, the enthalpy value will not be a correct one. So this is 64.6 kilojoule per kg, and this is 13.9 kilojoule per kg. So next we have to calculate the volumetric flow rate. So I think that is the step 3. Volumetric capital V is equal to, you have seen the formula A by 2, that is half the area of the door, into velocity into the door opening details, into velocity. It is given in the problem that the door is opened for 15 minutes per hour. The door is open for 15 minutes per hour for a shift of 12 hours per day. So into 15 minutes per hour into 12 hours per day. Let me write it. 12 hours per day. So the area, the width and the height of the door are given. W into H divided by 2 into velocity is already calculated in the previous step. This is the velocity, 0.6 meter per second, multiplied by the same thing, 15 by 60 per hour into 12 hours per day into 12 by 24. This is, I think, 2.44 meter, the width, and height is 2.74. 2.44 and 2.74 divided by 2 into 0.6 into velocity is 0.6 meter per second into 15 by 60 into 12 by 24. So the volumetric flow rate comes to, this is not velocity, this is volumetric flow rate. That's why for velocity I have written the full form, velocity. But here in the first step, here this is velocity, and step number 3 it is volumetric flow rate, because for both the terms we use capital V. It's better to write it and then write the symbol. So the volumetric flow rate comes to 0.25 meter cube per second. Meter cube per second. Now we can calculate the infiltration load. That is Q suffix capital I, that is equal to rho into volumetric flow rate into delta H. Rho into volumetric flow rate into delta H, which is equal to rho into volumetric flow rate into H2 minus H1. Here, this is volumetric flow rate. Volumetric flow rate. So substituting the values, Qi is equal to rho is the density. Rho is the density of air. You have to take it as 1.23 or 1.2. Density into volumetric flow rate is 0.25 meter cube per second into delta H. H2 is 64.6 minus, I think, 13.9. H1 is 13.9. H1 is 13.9. So when we calculate, we get 15.6 watts. 15.6 watts. So this is the infiltration load for the data given in the problem. So before I conclude this lecture, I just want to show one table which I have taken from the ISHRE cold storage design handbook. So here this is a table that is called table number 2.9. So this is volume in meter cube. And this is the air changes per hour above air changes per hour. There is a term called ACH. That means air changes per. This is normally used when we are calculating the ventilation load. It is called ACH. Number of, how many times the air is changed per hour. Air changes per hour. So the second column, this is the ACH value. This is also ACH. This is also ACH. This is greater than 0 degree centigrade. Sorry. This is for above 0 degree centigrade. And this is for less than 0 degree centigrade. And same values are given on the, since the table is too long, I have split into two tables. This is according to the volume. This is air changes or for greater than 0 degree centigrade, and this is air changes per hour for less than 0 degree centigrade, and this is volume in meter cube. Once, if you know the volume of the room, that is obviously the length, width and the height, if you multiply 3, you will get the volume. Accordingly, if the application is positive temperature application, we have to refer the second column for number of air changes per hour. If it is a negative temperature application, then we have to refer the third column, that is this less than 0 degree centigrade. And according to the volume, if the calculated value is not there, we have to take the next highest value, and accordingly the air changes per hour can be found out, which can be used when you are calculating the ventilation load. So I just want to give this insight, and with this, let me conclude this lecture. Thank you.